quantum field theory, gravitational physics, statistical physics, theoretical and observational astronomy, ultrafast spectroscopy, and advanced materials, including nanomaterials, soft and biomaterials. It is pleasing to note that based on the quality of research publications in the year 2019-20, the center stands among the top 3 DST institutes as per the Nature Index. In the Technical Research Center, scientists are working towards the translational research and innovation for the transfer of research outputs for societal benefits. And I'm very happy to mention that the 6 technologies have already been transferred in last 3 years to different startups and industries with a very strong relevance to the Make in India program. We have demonstrated that our invention on healthcare and biomedical instrumentation will make India self-reliant in some of the diseases prevalent in India, like anemia, neonatal jaundice, and oxygen deficiency. Even at a very short notice, we took the challenge to combat the COVID-19 pandemic and transferred 2 related technologies, one on an active respirator, which is known as the Bose Shield, and another one on long-lasting sanitizer known as Bose Tiger, which have been launched commercially about a month back and now available in the market on the shelf. On the New Year Day, the birth anniversary of Bose is celebrated every year with distinguished lectures and science outreach programs. We still cherish the memory of celebration of 125th birth anniversary 3 years back, which was marked with a memorable opening address by the Honorable Prime Minister of India through video conference, and gracious visit and address by Dr. Harshvardhan, the Honorable Minister of Science and Technology, Health and Social Welfare and Art Sciences, Professor Ashutosh Sharma, the Secretary of Department of Science and Technology, and many other dignitaries in the campus. The ceremony on 1st January 2018 at the center also included the release of a special cover on Bose by the Department of Posts, Government of India, the premiere show of a documentary film, An Iconic Genius, on life and works of Bose, produced by the center, and the inauguration of a new Bose archive and museum. It was our pleasant place to start the 125th birth anniversary of such a brilliant mind with distinguished programs that included the visit of Professor Wolfgang Ketterle, the Nobel laureate on Bose-Einstein condensation, organizing public and distinguished lectures, conferences, seminars, winter schools, summer schools, and most importantly, more than 125 science outreach programs in schools and colleges across the nation. Last year, we celebrated the 127th birth anniversary through 24th S.N.Bose Memorial Lecture delivered by Professor Supriya Datta, Purdue University, and a distinguished lecture by Professor Devashish Mukherjee, the S.N.Bose Chair Professor of the Center. The new Bose Archive and Museum was also opened for the public last year by the granddaughter of Bose on this day. This year, the 128th birth anniversary is being celebrated on the Golden Jubilee occasion of the Department of Science and Technology, and we are very happy that this event has also been identified as one of the theme events of the Ministry of Science and Technology for the month of January 2021. We are looking forward to the Silver Jubilee edition of S.N.Bose Memorial Lecture to be given by Professor Zeilinger and the Lecture on History of Science, which will take immediately after this inauguration function. With this, I welcome you all again to the online celebration of 128th birth anniversary of Bose, and hope that we all will be enriched by listening to the distinguished speakers on this auspicious occasion. Thank you all for joining this program online. May I now request Professor B.N. Jagtap, Professor, Department of Physics, Bombay, and the Chairman, Governing Body of the Center, who is the chief guest of this program, to give his inaugural address. Thank you.
Thank you, Professor Roy. Professor Zeilinger, Dr. Rajendra Singh, Professor Samit Kumar Ray, distinguished invitees, faculty and staff of S.N.Bose Center for Basic Sciences, students, ladies and gentlemen. At the outset, let me greet you on the occasion of 128th birth anniversary of Professor Satyendranath Bose, a genius in whose memory and honor this center was established in 1986. I compliment the director, faculty, staff, and the students on their efforts to make this center a place for advanced learning. I wish you all the best in your endeavors. The occasion is made very special since it coincides with the Golden Jubilee celebration of the Department of Science and Technology, which the department has been playing a pivotal role in promoting science and technology in India since its inception. As we begin this function on the onset of the new year 2021, I wish you all 2021 that is a lot better than 2020. Let me add my words of welcome to Professor Zellinger, a pioneer in the field of quantum optics and quantum information, and who has been decorated by many prestigious awards for many of his cornerstone contributions. I was also delighted to read that the name of his sailboat is 42, the answer to the ultimate question of life, the universe, and everything. His august presence on this 120th birth celebration of Satyendranath Bose is very special, since 128 is also known as the angel number. I welcome Dr. Rajendra Singh, a well-known science historian and science teacher. His scholarly writings have unraveled many unknown aspects of Indian science and scientists. It was given to Satyendranath Bose to make an important discovery and write a paper of 4 pages which had far-reaching consequences in modern physics. He earned a permanent place in the vocabulary of science: boson, Bose statistics, Bose-Einstein condensation, Bose stimulation, and also Bose-nova. Bose derivation of Planck's formula came at a transition point between old quantum theory of Planck, Einstein, Bohr, and Sommerfeld, and the new quantum mechanics of Heisenberg, Dirac, and Schrödinger. A hallmark of S.N.Bose's life and work was that he always had to negotiate with such transitions throughout his life. Seen from these perspectives, his work finds a very special place in the history of science and the history of modern India. Let me take you to the middle of 19th century, when the modern science, as we know it today, was introduced as a subject of study in a major way in Europe. The model of laboratory science and research school, as formulated by Liebig at Gießen in 1839, had a major influence on the universities in Europe. Jagdish Chandra Bose and Acharya Praful Chandra Ray were trained in that newly developed model of university education in England. Thanks to these stalwarts, scientific research began in India. However, the Calcutta University started awarding postgraduate degree in science subjects only in 1914. This transition facilitated young, bright students like S.N.Bose to pursue higher studies in science in India without having to go to England during the World War I period. S.N.Bose was one of the first homegrown modern scientists of India. It was also a changing time when science was making rapid strides, with relativity and quantum physics taking the center stage of research. Research in modern sciences in India at that time was difficult due to very little access to the literature and non-existent laboratories, so the theoretical research was the only solution. The next turning point in his career was his appointment at Dhaka University. He was uncomfortable with the derivation of Planck's law, which he had to teach students with its inherent contradictions, and felt it necessary to get a derivation without the inner difficulties. This quest resulted in the work, the Planck's law and the light Quanta hypothesis, and rest is all history that we know. This work is considered as the last major contribution to the old quantum theory, and in that regard, he attained the eminent place in the company of Planck, Einstein, and Bohr. His interaction with Einstein was another major turning point in his life. Thanks to Einstein, Bose's work became known to the world. Bose statistics was promoted, perfected, and defended by Einstein. It's also curious to recollect that it was Einstein who discussed the subtle issues and aspects of Bose statistics with the likes of Ehrenfest, Halpern, Owens, and Schrödinger, whereas S.N.Bose was not party to those deliberations. Yet another turning point was his visit to Europe to meet Einstein. However, he spent 1 year in Paris trying to work in radioactivity and X-ray spectroscopy. When he finally met, Einstein had moved to other things, including his work on unified field theory. And the long cherished dream of Bose to work with Einstein faded rapidly. As India was approaching her freedom, there came a transition in the objective of science in the country. Until then, the undefined objective was the nationalistic spirit and the romantic idea of serving the nation through science research and education. This objective gave way to the institution building and thereby the nation building. Leading scientists of that era were part of this movement and became institution builders. Bose, however, remained a classical academician who spent his career toiling away in university laboratories and classrooms and working for his students. The last turning point in his life was independence of India, the part of Bengal where he spent 26 best years of his life became a foreign country. There are a number of lessons we learn from the life and works of S.N. Bose. He was a true product of the nationalistic movement of India. As he said, he wanted to put scientific knowledge to the use through technology for the benefit of people or to contribute to science by intensive study. He remained an Indian to the core. His life reflected the true spirit of India. He felt himself responsible for his students, and for them, he even changed his research interest. He faced several transition phases and came out a clear winner. He was a homegrown scientist who made it big in the field of science. He was a rishi in the sense we worship those, the embodying the Indian thought, Asmai Swalpam Samajaya Sarvaswam, which means a little bit for me and everything for the society. All these lessons are so important for us today, and they will help us to respond effectively to the call of Atmanirbhar Bharat. On the 120th birth anniversary of S.N. Bose, we also need to reflect on the contribution of Indian scientists to the Bose work and related fields. While Bose-Einstein condensation was realized in 1995, a study shows that during 1982 to 2005, of the total 5,258 papers were published on this subject, the Indian contribution was merely 1%. And these contributions were primarily theoretical or collaborative work done abroad. Bose condensation has been breaking new grounds. We will be hearing it from Professor Challenger, and also in terms of the dark energies and gravitational waves, prospecting subsurface minerals, so on and so forth. Interestingly, this year itself, Bose condensate was prepared in space. On this backdrop, it is disheartening to observe that the land of S.N. Bose is far off from these developments. Indian biographers of S.N. Bose clearly ignore this issue and write poetically S.N. Bose, a forgotten hero. He is forgotten in the context of Indian research and not in the context of the world of physics, where he has been immortalized by several terms like bosons, Bose-Einstein condensation, and many other which I listed earlier. I strongly feel that this center, this institute can develop a vibrant program in many of these advanced areas to further science and technology in this country. This will be befitting to the name of S. Bose associated with this center. It may also be a good idea to institute an annual Bose symposium to discuss the latest developments and sensitize the young researchers. It could be an extended version of this function, and I'm sure that S.N. Bose Institute shall undertake some of these activities in some suitable form. Finally, I thank the director, faculty, staff, and students of S.N. Bose Institute for giving me this opportunity to join this very special function and share my thoughts. I hope to meet you all in person very soon. With these words, I declare the function open. Thank you very much.
Thank you, Professor, for a very inspirational word and giving a brief history of the science across the globe during S.N.Bose's time. And definitely it's a very good suggestion to have the Bose Symposium, annual Bose Symposium. I understand that we used to have some Bose Symposium earlier, but of course, with your guidance, definitely we can start this and we can have a Bose Symposium annually throughout India and try to take some of his so-called the legacy to the forefront of Indian science. So thank you very much for your time and inaugurating this event. Now we have the pleasure to have the 25th S.N.Bose Memorial Lecture. This is the Silver Jubilee version of the S.N.Bose Memorial Lecture. And this is the most coveted lecture series of the center. We have several memorial lectures. Out of that, of course, this is the most coveted one in the name of the Professor S.N.Bose. So in this case, I have the privilege of introducing today's memorial speaker, Professor Anton Zeilinger. Professor Zeilinger was born in Austria as an emeritus and is currently an emeritus professor of physics at the University of Vienna and senior scientist at the Institute of Quantum Optics and Quantum Information, Austria. He is currently serving as the president of Austrian Academy of Sciences. Professor Zeilinger is a pioneer in the field of quantum information and of the foundations of quantum mechanics. In 2008, he received the inaugural Isaac Newton Medal from the Institute of Physics, UK, for his pioneering conceptual and experimental contributions to the foundations of quantum physics, which have become the cornerstone for the rapidly evolving field of quantum information. He has received numerous awards and fellowship. It is too long to read here, but just to mention that he received the 2010 Wool Prize in Physics. Professor Zeilinger realized many important quantum information protocols for the first time, including quantum teleportation of an independent qubit, entanglement swapping, hyperdense coding, which was the first entanglement-based protocol ever realized in the experiment, entanglement-based cryptography, one-way quantum computation, and blind quantum computation. He is most widely known for his first realization of a quantum teleportation of an independent qubit. He later expanded this work to develop a source for freely propagating teleported qubits, and most recently, quantum teleportation over 144 kilometers with the two Canary Channel Islands have been demonstrated. It will not be very irrelevant to mention here that his ex-PhD student, Professor Jane Pan, Chinese Academy of Sciences, has made recent breakthrough in photons-based quantum computing, claiming quantum supremacy. I was listening to Professor Zeilinger's television interview probably about 15 days back, and he was so satisfied with the performance of the group that he has mentored. So thank you, Professor Zeilinger, and we welcome you for this S.N.Bose Memorial Lecture.
Thank you very much, Professor Kumarai, and I thank you very much for your kind invitation. At first, I wish you all a Happy New Year. I don't know if everybody in India is celebrating New Year today. I suppose there are also other days of New Year, but the 1st of January is become something more general all over the world. I very much trust that in the new year we will be able to meet in person again. I look back to a number of nice visits I had to India, and I really like your great country. I would also like to thank Professor Yagatab for the introduction, which told me a lot about the connection of science and India and Indian identity and so on. I really believe that science is both important for national identity, not so much to be better than others, but to provide a cultural basis. To me, science is part of culture, and we all over the world, whenever I meet people from other countries, we immediately speak the same language. I don't mean English, but we immediately have the same values. It's our curiosity, it's our intellectual openness, and all this. And in that sense, again, thank you very much for inviting me today. Is the sound okay? Can you hear me well enough?
Yes, it is. It's
Okay. So I will now start my presentation. I have it. Wait a minute. Here's my PowerPoint presentation, and I should start it at the beginning. No, I'm sorry, I was not intelligent enough to start it correctly, so I have to go up here. Wait a second. And start it here and start it this way. Okay, so again, thank you for the invitation, and it gives me a chance. It gave me a chance to reflect on the roles of Einstein and Bose in some of my work, which I did with many people, and to see that Bose has been important to quantum information, not only through the famous Bose-Einstein condensation. Now, just a small introduction. What you see here is a picture taken on the island, on a Canary Island of Tenerife, which is about 200 kilometers west of the coast of Africa. This telescope is operated to test optical communication with satellites by the European Space Agency, and we used it to test quantum communication. Now, to set the stage a little bit, there's an interesting parallel between Einstein and Bose. Einstein introduced, as you certainly know, in 1905, the concept of particles of light, which were later called by Lewis, about 20 years later, photons. Now, it's interesting that Einstein called only this work very revolutionary in a letter to his friend Habicht at about the same time. And it is also well known, but maybe worth mentioning, that Einstein got his Nobel Prize for the particles of light and not for any other work. And finally, it is also worth mentioning that the most often quoted paper by Einstein today is his famous work on the Einstein-Podolsky-Rosen paradox, which also has to do with fundamental quantum predictions for particles. Now, it's interesting to see what Einstein said about 20 years later. I want to spend the rest of my life thinking about the question what light is. Now, when we come to Bose, this is a picture of Bose from 1925, which I found on Wikipedia. This famous paper by Bose, which has already been mentioned by Professor Jagertab, Planck's law and the hypothesis of light quanta, was he sent it to Einstein, and he wrote this actually nice verse. Though a complete stranger to you, I do not feel any hesitation in making such a request, namely to publish this paper in Zeitschrift für Physik, because we are all your pupils, through profiting only by your teachings through your writings. I think it's fair to say that Bose also became one of the persons whose pupils we all are. Einstein translated it, as you know, in published it in Zeitschrift für Physik. At that time, you could only publish in German in that journal. And it's interesting to note that the paper has only 4 pages. And this is very often a sign of significant pages. I would like to lament a little bit about today's habit that papers have become very large, very long, have appendices and supplemental material and so on. Both didn't need that. Now, I want to come to some fundamental discussion, which is important for me. To this, sorry, it just says that my presentation ended. Someone else has started sharing.
Yeah, it came out of presentation.
I start again.
Again, yes.
I go ahead with where I was. Here we go. Is it okay again?
Yes, it's coming probably. Yes.
Okay. Okay. It's the famous double-slit experiment, which Feynman called the central mystery of quantum mechanics. This is taken from the Feynman lectures, the famous question. You have 2 slits, you have an electron gun, and when one of the slits is open, only you have either this probability distribution or this one. When you open both, you get the maxima and minima, which are due to interference. And the famous puzzle is what happens when you do the experiment with individual particles, one by one. Maybe you detect one now, you detect the next one tomorrow, and the other one 3 days later, and so on. There was a famous discussion, which I recommend everybody to read, between Einstein and Bohr, and it's written down in the Bohr-Einstein dialogue. You find it easily on the internet, and it's very recommendable to read it. And here you see the graph made by Niels Bohr, by a theoretician, but he knew that, for example, I'm an experimentalist mainly, as you know. Here the screws are very important. You know, Bohr did know that the details in experiment are relevant, and they are really relevant because they keep the relative position fixed. Now, the point is simply when you have these 2 slits open, you get interferences. And when you close one, you get only a homogeneous illumination. And Einstein said in 1905, in a discussion in Salzburg, in Austria, he said that with single particles there should be no interference, because how should a single particle know whether the other slit is open or not? And this is one of the points where Einstein is known to have been wrong. The modern way to look, the old way to look at it is if you would send path the particle takes and get the interference on the same time, because any observation would destroy interference. The modern way is that interference arises if and only if there's no path information available anywhere in the universe. And it is not important whether someone takes note. It is the possibility to obtain knowledge about the path. This knowledge could be obtained by any observer, but it need not be obtained. Just the possibility of obtaining the knowledge precludes interferences. The discussion, which has not ended to date, and the discussion is still open, the discussion between Einstein and Bohr can be simply signified this way here. Einstein had the opinion that physics has to describe in all circumstances what exists, a reality independent of us. And Bohr's position was, the way I read Bohr, is to say that physics can only be about what can be said about the world. This sounds trivial, but it is of utmost significance. Now, the famous, I cannot avoid to also show the famous Schrödinger cat paradox, which you are all familiar with. The point is simply not to say that the cat is alive and dead. This is wrong language. The point is that the quantum state describes the superposition, simply saying that there is no information present whether the cat is dead or alive. As soon as you look at it, you have the information, and that's it. Now, just to show you some experiments, this is an old experiment which we did long time ago, a single and double-slit diffraction of neutrons. This is a double-slit pattern, two-slit interference, just the way you saw it in the beginning in the Feynman lectures. The important point is, this was really done with physical slits, which you can easily observe and watch and look at with your eye, and so on and so on. The important point is, if you look at the intensities here, the intensity here is 4,125 minutes. This means simply that when one photon when one neutron is detected in a detector after the double slits, the next one is still sitting in the uranium nucleus, waiting for fission to happen. So really most of the time the apparatus is empty. Sometimes a neutron passes through and you get the interference pattern. The solid line here is first principles quantum mechanics, very straightforward. So we know, this is just according to the modern way. We don't know which path this particle goes through, and we get interference. This is also an experiment done a while ago with carbon-70 molecules by us in Vienna with Markus Arndt, who was our leader in the experiment, my senior postdoc, and here again, single particles and so on. The question is are there any limits in size and so on? And my personal viewpoint, these limits are only given by technological ability, and there's not any fundamental limit. At that time, actually, I should mention there existed papers which claimed that for such large molecules you would not see interference because of decoherence, interaction with the environment. And the way I always read such papers is the papers are correct, but maybe the assumptions can be overcome by a clever experiment. And this is the program for the future. There's no reason, there's nothing to see where this should stop in principle. Now we come to the photon, and we slowly come to the connection with Bose. Now consider just a single photon source. Such sources exist now. They have become standard in many laboratories. And consider a beam splitter and two detectors here. Now, the state of the two photons is described by a superposition, 0 and 1, which is also called a QuBit node. The point simply is that the photon does not make a decision whether to go here or here, but it's the measurement process which collapses the wave packet and which produces a result here, 0 or 1. Now the point is, Heisenberg already pointed out that these events are random. They are objectively random in the sense that there is no hidden cause. There is no explanation within physics, and I believe this will stay for us, at least for a very, very long time. There is no hidden cause for why this detector happens for a specific photon and this for another photon. And this is the famous measurement problem in quantum mechanics, and there is no explanation. You can have decoherence, which will lead to a non-coherent mixture of 0 and 1. But again, which specific result is obtained is outside current science. By the way, these random numbers, I claim, and I have no reason I have all reason to believe that are the best random numbers you can generate, better than any mathematically generated random numbers. Now, Einstein didn't like randomness, as you know, and he said also in a letter to Max Born that he's convinced that God does not play dice with the universe. I would love to hear his opinion today with all the technological progress. Another point I want to introduce before I come to the connection with Bose is entanglement introduced by Einstein, Podolsky, and Rosen in 1935. As I said, the most frequently quoted paper today by Albert Einstein. And it simply says that two objects which have been interacting later on in quantum mechanics cannot be described by, with few exceptions, cannot be described by their own specific states, but they have an entangled state. Schrödinger in 1935 really realized what this means, and he realized it the best, I think. He's called entanglement. He said, I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. And he already said that for entangled particles, only expectation catalogs for joint properties exist and not for individual properties. This is modern language. Expectation catalogs can, in modern language, be interpreted as information. Now, here's a way how to, it shows you how to produce these entangled photons. A picture of Paul Queert, who was my postdoc at that time. He's now a famous physicist. We have maybe I show a little bit more. We have a laser which pumps a nonlinear crystal here, and the nonlinear crystal is a picture of the radiation produces pairs, and these pairs of photons are entangled. They are entangled in polarizations. These are now the four possible base states, and this is now important because it connects us to Bose. These are the four possible states which can be generated in this specific type of down conversion. There are, you see, either the two polarizations of the photons are the same, they are both horizontal and vertical, or both vertical, and these two terms can be superposed with a plus or minus. This gives you two orthogonal states, and or the two polarizations are different, and the superpositions can be plus or minus. Now, the interesting point is that these states are symmetric upon exchange of the two particles. So if you exchange 1 and 2, this is symmetric. If you change 1 and 2, it's the same. So these are symmetric. Of these two states, only the one with the plus sign is symmetric. The one with the minus sign is antisymmetric. Okay, if you exchange H and V, you get the same state as before, but with a minus. Now, the point is, this simply means that symmetric states are called Bose states, as you know, and antisymmetric or bosonic states. Antisymmetric are fermionic states. You might so one of the states is fermionic, the other one are bosonic. You might immediately ask, how is it possible for photons, which are bosons, to have a bosonic state, a fermionic state? Now, this is simply possible because this is not the full state. There's also an external state, a state describing the propagation path. And if that state is also antisymmetric, then the total state can still be symmetric. But important is this feature now for us. And here is for the bosonic states, an interesting statistical phenomenon. You have a beam splitter here, and the same as before, a 50-50 beam splitter, and you have two photons incident. And what happens? Let's consider this bosonic state. 0 and 1 can be the two polarizations. And what you have in that case is that the two possibilities that both photons are reflected, are transmitted, or both photons are reflected, are destructively interfere. That means that you cannot have a photon out here and a photon out here. Simply means that both photons have to occur together, either here or either here. Now, this is a famous Hongu-Mendel dip. Here's the picture again, the source, the beam splitter, the detector, and here's the detection coincidence rate as a function of time difference. And you see there's some detection rate, which is just accidental when the time difference is large because the photons can be distinguished. But when the path difference becomes zero, the photons cannot be distinguished upon the arrival on the arrival time, and you have zero coincidences. So this is very nice. Interesting, but unfortunately it holds for all 4 bosonic states, not only for this one, but also for the other 2. So this feature cannot be used to identify a specific state. But the fermionic state, which is antisymmetric, has the nice feature that the 2 possibilities interfere constructively with probability amplitude unity. This is schematically simply written like that, and which means that the photons only come out in different detectors. And the coincidence rate here looks like, here again, they are indistinguishable, but then the coincidence goes up and it becomes practically 1. This was about the number of pairs emitted. Okay, so if you detect simply, if you have 2 photons incident on a beam splitter, and when you detect them afterwards in different detectors, then you certainly know that you have an incoming antisymmetric state. And this solved a very important puzzle for doing some of the early experiments. For example, dense coding, as it was mentioned kindly in the introduction. Dense coding was the first scheme realized for using quantum entanglement for an information scheme. You have a source which produces these entangled states, and then you can, using lambda over 2 and lambda over 4 plates, you can introduce, you can switch this unitary operation, can switch this entangled state to any other one. And then you have here a beam split, and you want to find out what is the case. Now, simply, if you have 1 photon here and 1 photon here, you know it's the antisymmetric case. On the other case, when both photons go here, you have 2 possibilities. This is a polarizing beam splitter. Either they have the same polarization or they have different polarization. If they have different polarization, which is just this state here, then they arrive at this detector and this detector, or this detector and this detector, and you know that you have projected on this other entangled state. When you have 2, when you get no coincidences, both photons are here, both here, both here, both here, you have projected onto a mixture of the other 2. So you can identify 3 different possibilities. But again, it goes back to this Bose characterization of symmetric and antisymmetric state. This is also important in quantum teleportation. I don't want to go into details here. In quantum teleportation, where you teleport a quantum state using an entangled state, and where you do here a Bell state measurement, just what I talked about now, and using that information you can apply a unitary operation on the other side and get the original state. Here's the mathematical machinery, which is not necessary to discuss right now. Important point is this classical information here. Now, teleportation has been realized in many ways. Quantum teleportation, I just focus here on the polarization-based ones. We did an experiment in between the Canary Islands, and the world record is now with the group of Chia and Wei Pan, who did teleportation using the Mitzius quantum satellite. So we are on a distance of the order of from 100 kilometers to the order of 1,000 kilometers. Now, in my eyes, the most important and interesting feature here, which fascinated me all the time and still fascinates me, is the teleportation of entanglement. Already mentioned by Bennett et al. in the original paper and explicitly proposed by us in '93. The idea is simply you have 2 sources of entangled pairs and project 1 photon from each pair to a Bell state measurement, which is the measurement of an entangled state. And that way, you erase the identity, basically, of the sources. you cannot tell anymore, if you do it correct, I cannot tell anymore whether photon 2 came from here or here, and which photon was which means that you entangle the outer two ones. You entangle two photons which have never been interacting. This feature is, by the way, an important conceptual ingredient into the quantum repeater, but I'm more focusing on the fundamental issues now. Here's an experimental realization done. You see, Jian Wei-Pan was still in my group at that time, and Thomas Jennewein was also a leading person. He's now in Canada. This is just a realization with fibers where an in-fiber beam splitter does the work. But it's just what I mentioned. Now I come to a conceptually interesting point. And this was proposed by Asher Perez. Asher Perez, a famous Israeli physicist who unfortunately passed away much too early, who said, well, let us consider the following situation of entanglement swapping. Let us consider two sources. And let's, as we said, let's register one photon from each source to immediately to a measurement of its polarization, right away after it was emitted. And then let us make a decision here. Here, the third, these are called Alice and Bob, and the third party is Victor. He decides, after these two photons have been registered, whether he chooses to use an apparatus which projects the two photons onto an entangled state, in which case these two photons are, after the fact, projected onto an entangled state too, or after the registration. Or you decide to measure these two photons separately, and that way these two are not entangled. Rather, one remains entangled with two remain entangled with three. And you get here the possible results, various polarizations, right-handed, left-handed, horizontal, whatever, here too. And here you get either results for the two photons separately, or you get projection onto an entangled state. And the experimental results are all completely consistent. The reason is statistics. The reason is that the results here can both be in subsets corresponding to entanglement or in other subsets corresponding not to entanglement. The experiment was done by us a while ago. I don't want to go into details. You create pairs of entangled photons, measure one immediately, and the other one you project onto in a later state on an entangled state. It suffices to realize one of the entangled states, namely the psi-minor state. Here are the experimental results. With entanglement swapping on, you get correlations between these two photons. You see correlations in three what's called mutually unbiased bases: horizontal, vertical, right, left, or plus-minus polarization. Okay, and here you get here when you this indicates entanglement, because only when states are entangled you can have correlations in all three bases with sufficient visibility. That's a detail now. If you have no entanglement swapping, you get correlation only in one base. So this simply proves that the idea of Perez is correct. And to me, what it shows that the effects here, the events here, are registered. They are registered at an earlier time before we know what they mean. And so in a certain sense, the quantum state only is finally achieved when we do this measurement here. Before, there is no well-defined quantum state which can be assigned to the individual particles. So in a sense, to me, I know this is a radical position, but it tells me that individual events, are more fundamental reality than quantum state. Events are the basic cornerstones of building our picture of the world. We might come back to that at some other time. Now I come to some more modern development, namely multi-photon entanglement. For example, a famous case of multi-photon entanglement are so-called GHZ states, states which are superpositions of two terms, but each one of, in this case, is a 4-photon GHZ state, vertical, horizontal, horizontal, vertical, plus horizontal, vertical, vertical, horizontal in different bases. This is not important. Simply meaning that all the individual photons are orthogonal in the two cases. This leads, as is known now, to very interesting statements about the statements of quantum mechanics contradicting the concepts of local realism, but that is not so important now. Important is that this kind of experiments, which we did in very early, opened up the field of multi-photon entanglement, which has become a very active line of research now. Here is an experiment which we realized such 4-photon entanglement. Without going into details, when you get a coincidence in these 4 detectors, you know that a 4-photon entangled state has been created. That's a picture from that experiment, which actually showed up at the front page of Nature at that time. Here's another experiment where we show 3-photon entanglement also very early. The basic point simply is that when you look at correlations for example, in this case, between 3 photons, horizontal and vertical polarizations, then quantum local realists predict that in such states only these correlations should exist for the 3 photons, only these correlations. Quantum mechanics predicts just the opposite, and the experiment confirms within experimental certainty the quantum prediction. The point now is that these states have become a cornerstone also in discussions in the development of quantum information tasks, quantum computation, etc. I now want to ask. I just showed you in principle how you can go. This was the idea again. How you can go to multi-particles by simply adding. In this case, we have 2 sources, but we can have also more sources, and we erase in the proper way the information from which source a particle comes, and you can have then multi-particle entanglement. This is the basic idea. But the question now comes up how to go to higher dimensions. So far, we lived in all our experiments, which I mentioned, we together, you, the audience, and we lived in 2 dimensions only, horizontal, vertical, or 0, 1, as signified by a qubit, etc., etc. Now, one of the there are two ways two common ways to go to higher dimensions. One way, which I don't go into detail here, is to use multiple beams. To have a photon not just in a superposition of 2 paths, but 3, 4, 5, 6, 7, you name it, and it has been shown that this kind of entanglement can be created also directly through this linear process of parametric down conversion. A very elegant way is to use donut modes. Donut modes have been long overlooked in physics. Their classical solutions to the Maxwell equations. There were only, I think it was 1996. I should have the reference here now. I'm sorry, this is another slide. By the group of Wordman in 1996, they were rediscovered. They have a wavefront, which is a screw, like shown here. This should be a screw. And when you project the intensity, you get this kind of donut. In the middle of the screw, the face goes around the screw in multiples of 2 pi, certainly. This is the axis of the screw. Multiples of 2 pi. Therefore, in the center, there's a singularity. The phase singularity, and thus the intensity there has to be strictly 0. And so when you project the intensity, you get these beautiful donuts here around the singularity. And the interesting point is that depending on the pitch, you can have a different pitch of the screw, which means that classically speaking, the phase goes around here once by 2 pi, or 2 times 2 pi, 3 times 2 pi, you name it, and so on and so on. Okay? Quantum mechanically, this implies when you look, you can realize these states for single photons. When you realize this state for single photons, then a single photon can carry either 0, it's called external angular momentum, orbital angular momentum with respect to the propagation axis, has either either 0 angular momentum, or the individual photon can carry, besides the polarization, this is a completely independent variable, can carry plus or minus 1 h-bar unit. These are the h-bar units of angular momentum, or plus minus, and 2 minus 2, and so on, up to arbitrary dimension. And the generation of this is just the way we simply do it. You have this nonlinear medium, the way I showed you before, and you create pairs. And these 2 pairs are in superpositions in these states. In principle, arbitrarily high angular momentum, and then some geometric factors and so on come in, which limit the magnitude. But anyway, this way we can create, number one, we can create photons with carrying very high angular momentum. In one experiment, we showed that a photon can carry 10,000 h-bar units of angular momentum in an individual photon, and that this can be entangled and all these kind of things. Here's again a picture of the various modes which you can have. Okay, various pitches, various modes. There are very interesting properties of these modes. I don't want to go into details, and it's clear that this additional degree of freedom opens up new avenues in quantum information. Just for example, if you have 2 photons defined in 10 dimensions, then this gives you 10 to the 24 different possibilities, and the same is with 32 photons and in 32 qubits. So there are scores of papers which talk about these possibilities. Here is a picture of some of these modes. They are also called Laguerre-Gauss modes. Here is the Gaussian mode, that should 1, 2 units, 3 units, and there are also modes with internal additional modes here, additional rings, which can be created. All this can be created by transmission through phase plates, as shown here, transmission of the photons through phase plates. Now, this opens up the possibility to higher dimensions. Here, now I come to some very recent experiments. In 2018, where we showed entanglement for a higher qubits. Here's the standard 3-particle entangled state for 2 qubits. which has various applications, as mentioned here, error correction codes, etc., etc. I want to refer to you to the literature here. Now, this would be a higher dimensional GHZ state. So all three photons are in the state 0, 0, 0, which can be something, it can be orbital angular momentum, it can be, you name it, it can be mode or whatever, 1, 1, 1, or 2, 2, 2. These three have to be just to be the orthogonal and distinguishable, the states. Now, it's clear that this has increased information capacity. It is also clear that you have new interesting tests of local realism. You can have new error correction, possibilities, etc. Now, what to do to go to higher dimensions? When we go just to 4 dimensions, to 4 particles, I remind you the scheme was, this is now a newer way to draw the same as you saw before. We have two sources, which produce entangled pairs. Okay, and you have a polarizing beam splitter here, and you project onto the case when you get a detection. You had, if you look at it schematically, in one source you create horizontal plus vertical. In the other one you also create horizontal plus vertical. And by looking at these coincidences, you erase the cross correlation parts. Okay? Sorry. Now this is already the next one. This is correct. How to implement 3 particle correlations, and this is now very interesting. You have to do some additional tasks to erase these additional features. There is an important feature is the so-called Leach interferometer, which sorts the angular momentum modes, not just like polarization did for horizontal and vertical, but in this case, it sorts it according to even and odd parity of the orbital angular momentum states, which is nice, but it creates a state where you get these features here, but you also get states which are mavericks, which are not in the GHZ state. And that is very interesting. That is a challenge. And the challenge was met by a computer program which was written by my former student. He is now in Toronto, Michael Krenn, who simply said, we were sitting together, and it was very difficult to design a scheme with additional beam splitters and so on, which gets rid of these terms. Okay, so he designed a computer program which takes as input of various tools and let the computer search for possible experimental realizations. And the interesting feature is, which I want to mention as the computer certainly found solutions, found also new ways to look at quantum experiments. The important point is that a number of the solutions which the computer found are solutions which a human, I claim, would never have found, because the best solutions do not reflect the symmetry of the state. Like the symmetry here of the state implies that it's a symmetry between 0, 1, and 2. And it implies every human would consider it important that the setup should also reflect the symmetry. But this is not the case. The best setups do not reflect the symmetry at all. Here's the realization. I cannot go into the details here. It's a complicated setup. We have here a high brightness 4-dimensional source, and we have here the generalization of the beam splitter to what is called a multi-port device. 3 inputs, 3 outputs, instead of before 2 inputs, 2 outputs, but the scheme is rather involved. I think I should not go into the details here, but what is done is exactly to get rid of the unwanted cross correlations. Now, this experiment was really a tour de force performed by Manuel Erhard in my group. Now we have 2021, so we can say already 3 years ago. Here is again a Melvin solution. That's the ideal setup. This is Melvin solution, which where we actually in the end came up not with 0, 0 plus 1, 1 plus 3, 2, 2, but with this state, which is also a GHZ state, right? 2, 0, 0, minus 1, minus 1, minus 3, 1, 1, 1, which are the orbital angular momentum states. The experimental results, this is just the density matrix from our measurements. I don't think that I should go into too much details here. A similar experiment performed more recently was the teleportation of a three-dimensional state, which is also, this is teleport now. The challenge is to teleport now this state, okay, and not just the two-dimensional state. Here is the input state, teleport is entangled additional state. And the point simply is that you have to create, additionally, you have to create a three-dimensional entanglement source, which is nice, but you also have to operate now with ancillary photons here and here, which is absolutely not trivial and was not foreseen in the early experiments. But lo and behold, this was done in the laboratory of G and Wepan, collaboration by us. Here you see Manuel Erhard, my student, collaborating here, and we get a nice result, clearly beating the classical limit. Really beating the classical limit. Okay, now I would like to come to another issue, which is also fundamentally very interesting, and like the other concepts which I talked about, is getting more and more applications in quantum information science. This is a picture, a paper published in 1991. It's a long time ago. It's now 30 years ago, nearly, by Zhu, Wang, and Mendel. Mendel had a famous laboratory in Rochester, which produced many results on fundamental properties, mainly of entangled states, but not only. He also did famous experiments about, for example, the undecidability in some cases that you cannot tell from which source a photon came from, and likewise. For me, he was one of the great experimental pioneers. Now, this is one of the experiments which we found extremely interesting. In a paper in Physics Today, 1993, Greenberger, Horn, and myself called this a mind-boggling experiment. The idea by Jeff Wu, but he was not a co-author at the experiment itself. The idea is simply that you take two nonlinear crystals and line them up such that one photon produced here propagates back through the second crystal, and you do it in such a way that by looking at this beam you cannot tell whether the photon came from here or here. Now, I go a little bit into the details. You have a pump, you create entangled pairs here, okay, maybe in different colors. This is just for the for some other possibilities. And you have here a second crystal, which also can create a pair. And I should say clearly that we create only one pair. We create one pair in a superposition of being here and being here. Strictly speaking, there are higher emissions, but like for all practical purposes, they can be ignored in such experiments. Now, if you can have here a phase shift, and if you change the phase and you look at the output here, you get a flat distribution, certainly no interference. But why do you get no interference? Because these two beams can in principle be used to find out whether the pair was created here or it was created here. And if it was created, then you have path information and you should get no interference, just as we said in the beginning. But now, if you line these crystals up such a way that the two modes are completely indistinguishable, this photon enters here, comes out here, or comes out here, and the mode here you cannot tell by no measurement, whatever you do here, whether it came from here or from here. And then you must get interference, because now the two sources are indistinguishable. And lo and behold, you get interference as indicated here, as seen by Mendel. And you don't even have to measure this particle, nothing, sorry. Nothing. You don't need to have any information. This can be used, for example, I mentioned a possible application. It can be used by inserting objects here, which influence either the amplitude, which influence the amplitude here. So if you reduce the amplitude here, and it passes through, then you know that the photon has rather come from here than from here. If you absorb completely, then it can only come from here, and you get no interference. If you have reduced it a little bit, then you get some interference, but with lower visibility. And then you can put a camera here, and you can take an image without the photon detected by the camera ever having interacted with the camera. The photon which has interacted with the object. This is now expanded in a nice research program by Sven Ramelow, who shows that you can use this feature taking images of biological objects. You here can use radiation, in long wavelength radiation, for example, even going towards microwaves, which do not destroy the biological object. But you get the image here in a wavelength where you have very good cameras. This is a very interesting development program, for example. But let me come back to fundamental issues, and this will now become the last part of my talk. I focused today on distinguishability and all these concepts. It's a concept actually more or less discovered by the computer Melvin. It's the idea of entanglement by path identity. Melvin was the computer program here. The idea is the following. I remind you, before we had these crystals here, these two crystals, and one beam enters the other one and then becomes indistinguishable. Now, in the new scheme, what you can do is you can have, these are the crystals now shown. The pump which goes here is not shown anymore, believe it or not. And the beams are shown bent. They're not shown straight as they usually are, but that is conceptually not important. And you have here two crystals which produce correlated photons, photon pairs, HH, but not entangled. Here also HH, but not entangled. Here VV, but not entangled. Here VV, but not entangled. And now what you do is you send this mode back into the second crystal, this one back into the second crystal. Now, if you detect a photon here, you don't know whether it was V or H. When you detect a photon here, you also don't know that it was V or H. But when you detect a fourfold coincidence here, then you know that this is a four-photon GHZ state, because of the possible correlations you get here. Now, this is very interesting because now you produce the entangled states very effectively. You don't have to use a trigger. You don't have to throw anything away. And the scheme is scalable. You can also play a scheme where you, for example, create 0, 0, 0, 0 everywhere, angular momentum, for example. Then you change here the angular momentum by 1 unit, here again by 1 unit, here again by 1 unit, and that way you get out the state. Here are some additional phase shifters or whatever you want to use. You can also cross the beams in different ways. This way you can create a 4-photon entangled state. Here you can 6-photon, a 5-dimensional entangled state, and so on. This is a new scalable way to produce complicated entangled states. And most recently, we succeeded just because my computer had a problem. I couldn't show the experimental results, but we succeeded. It was just published in PNAS to demonstrate this phenomenon as a source for high-dimensional entangled states. And again, this can be very interesting for larger dimensions. It also raises some very interesting fundamental questions, which we will publish in a future paper about when can you talk about the source or not. It goes back to the experiment I discussed proposed by Perez many years ago. I want to come to the end. This is a famous poster I found on Wikipedia, which says, Erwin Schrödinger is not wanted dead or alive, but dead and alive, but whatever that might mean. Here is an interesting statement, a very humble statement by Einstein. As I said, Einstein at some point said that all the 50 years of conscious brooding, said that I want to spend the rest of my life to think about the question, what is light? And here he said, it was a few years before his death, all the 50 years, I think 53, all the 50 years of conscious brooding have brought me no closer to answer the question, what are light quanta? Of course, today every rascal thinks he knows the answer, but he is deluding himself. This is very interesting, and it is not at all arrogant. It's a very humble statement in my eyes, very humble. Just to close, this is also quite interesting what I show you here. I apologize for the German language. As you see, it's a letter written in 1913 and signed by Planck, Nernst, the Nobel Prize winner, Rubens, and Wagner. Rubens was the guy who did the experiments for the black body radiation, which were, as you know, explained by Bose in a very elegant way, just assuming that the phase-space density is characterized by volumes of h to the third, or h bar to the third. It's quite interesting. Anyway, now what these people say is they have the honor to propose the professor at the ETH in Zurich, Albert Einstein, for ordinary member, regular member of the academy with a very good salary at that time. Okay? And then they say something interesting. I read it in German. The fact that occasionally in his speculations he did overshoot the goal should not be held too strongly against him. For example, in his hypothesis of light quanta, because without occasionally daring some risks, not even in the exactest natural sciences, you can introduce something really new. Now, today we might smile about this. This was 1913. It was 8 years after Einstein proposed his light quanta hypothesis. We smile about this, but remember, Einstein received the Nobel Prize in 1921 for this idea. And that is, I always like to say, is why I like to be a scientist. So even if the whole community is of a different opinion, facts and experiments, in that case, it was the precision measurements of black body radiation and of the photo effect, can convince the whole community and kill old ideas. And this is something which not all human activities share. So with that, I would like to thank you very much for your attention.
Thank you, Professor Gellinger, for a wonderful lecture and giving us the updates on some of the breakthroughs in the quantum information and quantum teleportation. I hope you'll be happy to take some questions from some of our audience. And before I request our team faculty, Professor Archer Majumdar, to conduct the question session as well as give a vote of thanks, I have a memento on behalf of the center. So we cannot present you physically right now, but we will be sending it to your address in Austria, and so that you remember this S.N.Bose Memorial Lecture and the community at the S.N.Bose Center. Thank you very much. Yes, sir.
Can we have the chat box up on the screen, please? Well, thank you, Professor Zeilinger, for such a fascinating talk. And let us see if we have some questions in the chat box.
Wait a minute. Can I open the chat box?
Yeah, I can. Yeah, let us see. Okay. Okay.
I
as far as
cannot open it. It says it is only
fine.
for team members.
Sure. So let me just ask the audience, does anyone have a question? So are all of them unmuted, Abhijit? Okay. So anyway, till the time the first question comes, let me ask you a brief question. So this was a very nice presentation about the developments of the question posed by Aisha Perez, on which you did an experiment many years ago and following on the most recent experiment. So philosophically, do you think that such experiments will go a long way to rule out realistic interpretations of quantum mechanics, such as the Bohmian interpretation, for example?
The question is whether such experiments rule out a realistic interpretation of quantum mechanics, right?
Yeah, in the sense that events being more real than quantum states, in the sense that only reality can be ascribed to events, but not to quantum states. So doesn't this way rule out such interpretation?
Well, I did not say that reality cannot be ascribed to quantum states. So therefore, I thank you for your question, because this can actually be a misunderstanding. Concerning the quantum states, my viewpoint is very much that of Heisenberg. He said that the quantum state are a representation of our knowledge. They are the representation of our knowledge about the situation, and therefore they are real in a certain sense. But the point is, they do not always describe real. They describe the possibilities of experimental results. So an experimental result is certainly real. This is my position, because in the lab I can see it, but this is something where we all can agree upon, that we have a certain result now. They describe possible experimental results and all possible experimental results, most of them only with probabilities. So in that sense, they describe potential, they describe a reality, namely the reality of the apparatus which has been built up. The apparatus sits there, and we have all the knowledge about the apparatus. We know how it performed earlier. We know what the laser does. We know what the beam splitter does, a detector does, and so on. And based on that knowledge, we can write down a quantum state, which is a catalog of all possible future results, and no more. And Heisenberg also says then that the measurement process, where we have to change the quantum state, just a simple case, as I mentioned before, with the beam splitter, or even in the Paris experiment, right? The measurement process means that we get an update of information, we get new information, and therefore we have to change the quantum state. And what would be more natural then to change the quantum state upon new information. This is just, but it is, so to speak, the representation of our knowledge. And what we have learned now, the maximum knowledge we can have. We have now learned that we cannot have more information than what is represented by the quantum state in a certain situation.
Thank you. Well, are there other questions from anybody in the lecture hall, or anybody who's joined online? Okay, so since I don't think the people might have facing some difficulties in connecting at this moment, so I should formally begin my vote of thanks for this whole session. Well, first and foremost, I would like to, thank Professor Zeilinger, and it gives me immense pleasure to thank him again for such a wonderful lecture. Well, Professor Anton Zeilinger is an institution in himself, and for those of you young students who have got into science much later, I should mention that he has been an institution for 3 decades now. When I actually started studying this subject more than 25 years ago, one of the first papers that I got across was the paper about GHZ states, and you have seen during his talk that this paper hasn't yet lost relevance. On the other hand, it has even become more relevant even after 30 years. So the GHZ states and GHZ theorem was a pioneering contribution of Zeilinger. And of course, Zeilinger's contribution didn't end there, and it took two very, I should say, different colors, one on the side of applications, the other on the side of foundations. In the application side, Zeilinger first performed the experimental dense coding in 1996, and this was soon followed by his group performing the first demonstration of quantum teleportation. Then came the first entanglement swapping experiment in 1998, the quantum cryptography with entangled photons in 2000, again the first experiment on one-way quantum computation in 2005, blind quantum computing in 2012. And on the other hand, on the side of foundations, of course, there was the first demonstration of a loophole-free Bell inequality test, which closed the communication loophole for Bell inequality. That came from Zeilinger's group in 1998. Then the quantum interference of macromolecules, which Professor Zeilinger briefly alluded to in his talk, came in 1999. And this actually has to do with, a collaboration or a related merger of ideas with Professor Leggett's work, and not only on macromolecules, but also Leggett's work on crypto non-locality that was first demonstrated by Professor Zeilinger's group in 2007. And in 2011 came the demonstration of quantum contextuality. So Professor Zeilinger has many firsts to his credit, and it will be too much for me to discuss all these firsts. But nevertheless, before ending, any description of Professor Zeilinger's work will not be complete without mentioning the work that he did during his PhD times on neutron interferometry in Professor Helmut Rauch's group. So it shows what a versatile set of skills Professor Zeilinger has actually inculcated over the years. And personally, it gives me another great pleasure to mention that we have had the privilege of hosting Professor Helmut Rauch at the S.N.Bose Center twice. And I would request Professor Zeilinger that when the situation improves, that he could also perhaps sometime visit our center, S.N.Bose Center, maybe during one of his visits to these parts of the world. So thank you again, Professor Zeilinger, very much for a wonderful talk.
Thank you. I would like to thank you again for your hospitality. I'm very glad that you mentioned Professor Rauch. He was really one of the pioneers of the whole field of quantum information. Some of the schemes he realized with neutrons have actually now become relevant for quantum information. It's very interesting. I can I could list this, but is absolutely at that time. I should say that the scientific community was not very open to such fundamental work, because quantum mechanics was considered to be understood. Well, it is understood, but in a sense, and nobody had the feeling that this would lead to such interesting technological applications. In any case, I thank you very much for your invitation, and I sure hope that the situation will change and I can follow up on that. Thank you very much. And I should also mention, particularly also for the younger participants, if you have questions, you can send me an email. I showed you the email in the beginning, but you also can find it on the internet easily. Just send me an email. I cannot answer everything immediately, but I will try to reply. Thank you very much. And again, Happy New Year.
Thank you so much. Happy New Year. So next I have great pleasure in thanking Professor B.N. Jagtap, who is the chairman of the governing body of the S.N.Bose National Center for Basic Sciences. And today, of course, is 1st January, and Professor Jagtap has tremendous other responsibilities. So we are extremely grateful to him for sparing his time on such an occasion and actually giving an inspiring opening presentation. And it should augur well for our progress during the current year, that we should, I think the center can play some role in the development of quantum science and technology. And I again thank Professor B.N. Jagtap for his inspiring address. Thank you very much.
Thanks a lot.
Thank you. And last but not the least, I should thank my director, Professor S.K. Ray, for actually giving us this opportunity to organize such events. And not only that, I should relate to you a history of this, because this year has been a difficult one for all of us. And Professor Ray was one of the first persons who actually inspired us or spurred us to come out of the lockdown mode and start our activities in the center. So when the unlock phase started, we were more equipped to actually carry out our further research activities. So thank you once again, Professor Ray, for your kind encouragement and enthusiasm. And finally, I should mention that this talk is, again, as it was mentioned at the beginning, that this talk is part of the DST Golden Jubilee celebrations, and DST has kindly included it in their charter for the month of January. So I should like to thank the Department of Science and Technology and acknowledge the support provided by them, and also Vigyan Prasar, who have actually very painstakingly made an effort to spread out, to circulate this lecture among wide audiences through electronic media and other channels. So thanks to both DST and Vigyan Prasar. And before we break for a short tea interval, I should like to remind you, all of those who are online, that we have another presentation at 4:30, that is about 45 minutes from now, by Dr. Rajinder Singh, which also promises to be a very interesting presentation, and I should like to thank him in anticipation as well. So thank you very much, and we break for tea now. We come back in 45 minutes time. Thank you.
Hello. I'm not able to hear you. Hello? I cannot hear anything. Professor Saab, hello. Nice.
You hear? No.
Yes, now I hear.
Now I can hear you. How are you? Good.
Very
Happy
fine.
New
And
Year.
you? So same to you. Nice.
Hello, I'm Supurna here. Nice
Hello.
to. Hello, I'm
Ah,
Supurna,
yeah,
Purnima's daughter.
thanks.
Suprakash Babu.
Yeah,
Yes.
I got
So,
the information from Rajinder Singh, so that's how I thought I'll join. And,
he did not get the same dress as Baba.
I just thought, yeah.
Suprakashi.
Yeah, Suprakash Roy, I think you have not met me. I think you have not met my
No.
sister.
Yeah.
Mr. Rai has, Professor Rai has met my sister, Sukanya.
Yeah.
Mhm. So I think the meeting is going to start soon, right?
Yes, I think in 5 minutes. Yeah.
Yeah. Okay.
Sure.